Yeah, but I do it on the Mac, so I don't have VBA. Can we also hear Dirk in Finland?
Hallo? Test, test.
And while Dirk is miking
Zo
up,
beter?
the next talk is from our intern, who
Not
is now
anymore.
our ex-intern and
Yeah.
will be our new employee. So you're now in the twilight zone of your career.
Sort of, yeah.
For 1 month, completely free.
Don't have to get any coffee anymore.
But Dirk was here on his internship for more than half a year.
Yeah, 9 months.
9 months. And looked into the query flows for Startpagina. It didn't make us any money yet, but we have high expectations of this.
Next month.
So it was really smart of him to not make any money yet, and then
So
wait until we offered him a job and he comes implementing it.
They had to hire
But
me.
that will start on January. So good luck.
Okay, thank you. So this is my second SaKE appearance. I don't know who of you were here last time in Hoofddorp. Only a few hands. I also, well, of course, there was a video made by my appearance. It got a lot of views, actually, well, for my presentations at least. So who saw this one? Who wasn't there? Okay, so who wasn't, or who didn't? So who didn't hear my story at all? That's actually the question. Okay, a lot. Luckily, I got a short recap of what I did, but it's only short. So I graduated on query suggestions for Startpagina. And I did that by making a statistical model based on historic data. And based on this historic data, I wanted to predict if people queried a particular query, what the chances were that they also would query something else. Now, this would be an example of historic data stored in query logs. So you have a user ID, a date and a time, and a query that the user entered at this date and time. And what I did with this is build a graph model. I will tell you more about this later, which might look like this. So each node in the graph is a unique query in the query logs, and the edges in between them mean that these queries were subsequent in the query logs at some point. And the edge weights are the number of times that this occurred in the query logs. Now, this is a really small example, an abstract example, but for 2 months of data, this meant that the graph was 14 million nodes big and 20 million edges in between those nodes. So this is a fairly large but very sparse graph. Now, what I did is if somebody queries query A, in this case, what I did is perform random walks, and a lot of them. And by performing random walks, I also counted how many times we walked across some other node. So, for example, we could do a random step to some other node from A, in this case to node F. And we would count the fact that we went to F, and well, in this case, we cannot walk any further. So we restart our walk. This time we walk to D. From D, we can go further to G. And now we can only walk to E. And again, we count the number of times that we visit these nodes. So we repeat this maybe 5,000 to 10,000 times. And based on this, we can make a probability distribution of, given we query someone queries A, how likely it is that they will also query someone in this graph. So in this case, F is very likely, and E, which nobody ever thought of querying after A, is probably also something that users will query. And based on this, we can make suggestions. So this is in a very small nutshell what the model was about. And well, I did the presentation a lot of times in the past weeks, and Jelmer and Sander asked me to tell something else, because they can pretty much do the presentations themselves by now. So I want to tell you something about the pre-processing I did, query logs, to construct these graphs. And yeah, that's what I'm going to talk about. Before we, no, I'll just continue. So the first thing to do with the query logs is to split them into logical search sessions. So if you're looking for something on the internet, you might try various queries before you actually find what you're looking for. Now, one of these, firing of these particular queries is a session. So I also formed this definition of it. It's a chronologically ordered set of queries that have a common search goal and are entered by a single user within a certain time interval. Now there are a few important aspects. They're chronologically ordered, so speaks for itself. It has one search goal, so if you change your mission, then it's not the same session anymore. A single user, of course, and it has to be in a time interval. If you don't do anything for a particular amount of time, then the session ends as well. So we have our query log in this case, and well, the ideal way to split this would be this. So in between the fourth and the fifth query, there's a different user. So this is a logical border in between the queries. And in this case, the user was first looking for lemon-related stuff and then switched to owl-related stuff. So it changed the mission. So this is also a boundary in the query log to start a new session. Now this is something we do for the complete query logs, of course. But what we also do, what we're also interested in, is the formulation type of the changes in the search mission. So if you can query something else, we're interested in what type of reformulation it is. So if you change from owls to snow owls, you type snow in front of it, then you make your query more specific. So this would be called a specialization. The other way around is a generalization, or generic query. You could correct spelling errors in your query or make small changes, which is the C class in this slide. And you could do a parallel move, well, switching from snow owls to forest owls, for example. And in the now specific, there's also a fifth reformulation type. And sorry? No, that's actually the C class. What people are doing, or what Startpagina does, is while you type, they already show the results. So you don't have to press enter to actually log the query. So what we do is, after the user doesn't do anything for 1 second, they log the query, and this enters some noise in the graph, and we would annotate this with the fact that people were still typing their queries. So this is the fifth type. Now, doing this and annotating this is, of course, for a small query log, you could do it manually. The graph is very large. For 2 months of data, it's over 70 million queries, so we're not going to do this manually, of course, especially since you want to update the graph at points in time, and, well, you would need a lot of students to get this done every day. So the idea is to create a classifier to do this automatically for you. Now, before I continue my story, I want to ask you, who is familiar with machine learning algorithms or techniques, or does something with it? Okay, it's a fairly small group. I will explain to you a very simple example of what you could do to teach a computer to do something for you. The first thing to do is to extract features, because you have some list, or you have some objects, and these objects have properties, and based on these properties, you want to make a decision on what type of object it is. So the first thing to do is to extract, or at least define some features that you're going to use to classify an object. Then what you do is you tell the computer about particular objects, what type they are. So you say, well, this object A is type 1, B is type 2. And based on that, you can train a classifier. And I will show you with an example I prepared. So let's see if this works. Oh. I have some Excels waiting. So say we're going to classify animals, and we're interested in if it's a small animal or a big animal. Now, one property we could use to do this is the weight of the animal, and I Wikipedia'd some animals and wrote down their average weights. So what we could do is add in this CSV a class field. And now for each animal, we're going to say if the animal is big or small. So an elephant, fairly large animal, let's call it big. An owl is pretty small, so let's call it small. And then the sheep, again, very small. A whale, pretty big. A human, I would say small in relation to some animals, considering the fact that humans are animals, maybe, or depends on what you think about it. And a rhino, which is a fairly large animal. So what we did now is we had some objects, in this case animals, and we told the computer how big or small these animals are. So I'm going to save this. And then we're going to go to our classifier. And this is a particular algorithm that I used in my research. There's many more. But I use a C5 classifier. I have my reasons for this. So what we first do is we read the data of, that I just entered in the CSV. And what we then do is train the model. Well, one line actually. We state that the class field, or the class field is the one that holds the objects that we're trying to classify. This is the training data that we're trying to train on. And well, we could have a tree model or a rule model. I'll back to that later. So we can train a model. And this is actually it. This is all we did. And what we now created is a model that help us in classify animals. So we have rules now here that says, well, if the weight is over 80, then we consider it to be a big animal. And if the weight is smaller or equal to 80, then we consider it a small animal. Now this is actually the basics of the whole machine learning thing about what I did. So now let's move on to some more complicated classes. So let's see if this works. Because now we're going to create the classifiers to split the sessions and to annotate the reformulation types. Now first we have to extract the features. So given that we have this query owls entered by user A at this particular time, what we do is we compare it with the query before this query in the query logs. In this case, it's owl's food. So the user made a more generic query. And we're going to extract features. Now, some of the features we used, I list them here. So just a minute ago, we only had one feature, the weight of the animal. But now we have many more. So we could check if the strings are equal. We could check for substrings or superstrings. We could go into words if people added words or maybe removed words. And many more of these, and also combinations of these. You could also combine, for example, how many characters a user entered divided by the time they took to enter this. So we extract all these features. What we then did is from the million queries, we draw almost 1,000 supersessions based on only the user ID and a 1 hour timeout value. And one supersession could contain multiple sessions. So we identified manually, this was a very tedious job, took me a few hours. And we marked the session boundaries. So we told the computer, well, this is a boundary, this is a boundary. And this looked like this. I wrote this console application thing. And I would say, well, query 11 would be a boundary. We go from some real estate query to a dietary query. And again, on line 9, do some tax-related queries. So I did this for all these 906 supersessions. And then we went on to train the classifier. Now I have some great Excel sheet. Let's see if I can switch. Yeah, I got some Excel indeed as well. It's a really Excel-related SaKE. So this is what it looks like. So we have the class column again, in which we have the fact that a query has a border or not. And then we have all the features we calculated for those query pairs. So this would say that the query apparently was a substring of the previous query was a substring of the current query. So we put all these values in there, and then we can again run this on R. We read the data. Oh, well, just a little bit, maybe. So we run this again. Now you see that we loaded all the 4,917 annotations, and then we can create the models. And I have the rule and the tree model. The rule model is pretty similar. Sorry. No. Rule model is pretty similar to what we did before. It's slightly bigger. So now we have 7 rules that say that Well, if the cosine similarity of the queries divided by the time is lower than this value, then apparently we say that, some Liebenstein distance, some other metrics are, in these ranges, then apparently it's a border. And what we could also see is that 263 of the cases of those 9,417 cases went through this rule, so the rule applies to this, and only 2 of them were not class indicated. So this is a pretty, you also see the value here, this is a pretty accurate rule to use. So we have much more rules, so this has slightly more issues with correct identifying. So we now have a set of rules that we can use to cases that arise in the query logs. What we could also see is that these were the significant features for specifying these things. So time difference is apparently a very important feature. So if users take a lot of time to formulate new queries, we now know that this is an important indicator for session borders. So this is how basically it works. You could also, instead of having rules, you could also have a decision tree. And a decision tree is, it's a tree, you all know a tree. And based on value is higher or lower, you go into either one of branches of the trees. And you could also use this for classification. It's really, for classification purposes, this is really good, but you often overtrain too soon if you do this. I'll show you this in the next example. So we can use this to classify our sessions. We also did this for the reformulation time notation. So we again draw a lot of subsequent query pairs, and we're always in the same session. And we again told the computer what type of reformulation was going on in this query pair. So we again manually mark this. So we have a nice other console application to do this. In this case, we have elephant and elephant tusk, and this is considered a specialization because you make your query more specific. So we annotate it with a specialization, and we do this again for 1,738 query pairs. Again, very tedious job. And we again get a nice Excel sheet with all sorts of features. We again have the class column with all the classes. Again, a very lengthy list of features belonging to these things. And then again, we go to R. We read the data. Now we have 2,000 objects in there, reformulation objects, and then let me first show the rule model. This is not right. I didn't run this. Oh, this looks better. So now we have, since there's 5 classes, this is a way harder classification. This also displays in the number of rules we generated. So now we have 38 rules that are used to try to classify these reformulation types. So apparently, if the length difference is really small, then and the number of edits to achieve the new query is really small, then apparently we have a class. And this is what this tells you, and we can have a very lengthy list in decreasing. Well, it's not decreasing order, but at least it gives you some indication of what rules you should fire or test first to do this. So this we can, I wrote a script that converts this to Java. You can get a Java method out of this that has these rules in it. And you can use this to classify the reformulation types. So the results of all this was that we could split the sessions with 83% accuracy. This means that we got the start of the session right, we got the end of the session right, and we didn't make any mistakes in between. So for this type of classification, this is actually really accurate. You could make this all more accurate by entering semantic relations in this, because now we look at lexicographical properties of queries, but you could of course also look at the meaning of a word to see if they're any way related. The reformulation type annotation was actually more accurate, especially the generalization. The same query and the parallel move are really easy to classify because the generalization often has queries that are shorter. So this was really easy. There was a lot of mistakes in between specializations and typing types because they're in some way related. Typing could also be considered a specialization. So most errors were made in that area actually. So we were also very happy with these results. So maybe you want to experiment yourself a little bit with doing these kind of classifications for your own work or make your own work a little bit easier. It takes a while to get some of your data trained, but if you use these tools, it's really a sort of a click and drop and click some things to get your own classifier going on. The only thing you have to do is of course train it, which could take you maybe a few hours, but after everything you do becomes way quicker. And that actually pretty much takes me to the end of the presentation. What I also want to say you is if you want to read my thesis, which is available at the TU Delft repository, you should go to this address and type in my name, and then you can read more about how this all incorporates in getting from the query logs to the actual query flow graphs, and I will build suggestions from that. So that's it.
Any questions for Dirk? And while we're doing the questions, could the next speaker start setting up?
Betcha, kucha, people.
I think that's you, Bart. Why do you thought I was looking at you?
We got a question.
Yeah.
Yep.
So I was wondering, so you mentioned semantics relatedness or semantics at the end. So are you planning to do anything with that?
Well, at this moment, I'm not. But well, at least I've seen in the literature also that this really could help to. Yeah. Okay. This really could help to. Yeah. Somebody was waving at me. This really could help to improve your classifier. For the session splitting, the difference was actually really small. So adding extra semantic information only helped in removing some false positives. Because we're really good at false negatives. There's really not a lot of false negatives, but false positives are plenty. So semantics could help to.
For instance, you showed this example of elephants, ducks, and then tree bark or something. That's something that you really could find the topic models of this semantics.
Yeah. Yeah, so especially for the reformulation type annotation, semantics would help a lot in making this better. Yeah.